are the top 5 SNPs, and these individual markers are not important, but the couple of things to note is that, for one, these are all on the chromosome 6p. They're all in the HLA region, so we're finding only these really strong associations among the top. And even more so, the ones that we're finding with the full data are really the exact same ones that we're finding once we recursively remove out the sparse variables. Essentially, we're not really gaining anything by recursively removing out information. What we found at the end, we found at the beginning. We're just getting rid of the zeros. And even more so, the overall error rate stayed constant throughout these at about 34%, suggesting that, again, nothing is really being gained by removing out sparse variables. However, when we run this now without chromosome 6p, something very different happens. And for one, when we first run it, the error rates are at about 48%, 49%, suggesting essentially a coin flip, that we're not actually doing very well at all with prediction. Our model is not very strong. Maybe a little bit of learning, but not very much. And the top variables really seem kind of like a random smattering. These are the average marginal chi-square statistics. But once we start removing out sparse variables, the error rate starts dropping dramatically, because now we're removing out the noise. We're not searching over irrelevant variables anymore. And our final error rate gets down to about 21%. Doing a 4th subsample, the error rate actually started to rise back up again, suggesting that we may have started removing out a little bit too much information. The other interesting thing is that now if we begin to look at the marginal chi-square statistic of the top markers, we start seeing ones rising to the top which show potential real associations. Now, these are all p-values, aside from this obviously this top one, these other ones are all p-values of maybe 10 to the minus 3, 10 to the minus 5, where in a typical context you may be excited about, but if anyone who works on genome-wide association studies, you kind of just, you laugh it off to multiple testing and say it's probably not significant. But so essentially what we consider is probably what's happening here is that we're just doing a reshuffling and a re-ranking of some of the top associations. We found a method that we're taking these that probably have an association, are probably going to be buried in a typical test, but here we're allowing them to rise to the top. Finally, what we also see is that the top ones here are a very different set from the top ones after subsampling, that the subsampling process really does allow new things to rise to the top. So the next consideration was what to do with this correlated data. And it's pretty well documented in the literature that based on the way variable importance is calculated, you can have a lot of problems when you have correlated variables. Essentially, if we imagine an extreme example, if we have 2 identical variables in our data set, then random forest or any card as a tree growing method does not care which variable it brings into the model. Sometimes it'll bring in one, sometimes it'll bring in the other. But once it brings in one of them, it will not bring in the other one because they're identical and it won't get any more information gain. So therefore, if you have these correlated variables, you can have an overall, the variable importance of each one will essentially be cut in half. So if we can prune out these correlated variables, but still cover the same region, perhaps we can be both computationally more efficient, but more importantly, allow these important associations that are buried at the bottom to rise more to the top. So to do this, a standard genetics package called Plink was used, provides 2 methods for LD pruning, a pairwise correlation, and then a sliding window multiple correlation. And 5 different levels of LD pruning were tested. And what these levels mean essentially is that as the overall R squared decreases, we're removing more and more data. The overall correlation in the data set goes from 99% down to 33%. So in terms of what this looked like, going across the x-axis is the degree of LD, and then along the y-axis in red is the final out-of-bag error rate after doing the sparsity pruning. And what we note is that looking at full data, LD of 99% and 90%, there really isn't that much loss of final error rate. However, once we start pruning to about 80% and then more, we do see a little bit, the prediction error does seem to go up. We do see a little bit of a beginning of loss of information. Just to give a little bit of context in terms of what may have been gained from this, here we have in the blue axis are the total number of SNPs in the data set, and we see that in pruning down to a level of 90%, we've essentially cut the data set size in half. For those who work with genetic data, this was done on an AFI chip, so you do expect there to be a high degree of LD, and this is essentially what was documented here. had I done this was a Lumina chip, you may not have expected that much pruning to have happened. But as it were, we were able to remove out a lot of data. But in terms of thinking about now which of these three configurations is best, there's actually no inherent reason to prefer one over the other. All three are doing equally well in prediction, so in theory, they're all equally valid data configurations. What does it look like? So of the top 25, the average margin was pretty similar, and this actually difference is really just due to one strongly associated SNP that was pruned out. So indicating that they're all finding fairly strong results, not top things, but things that are probably strongly associated, but maybe buried in a typical analysis. So the next consideration was, well, how interesting are these SNPs? Are they potentially functional regions? Do these exist in genes? So again, looking at the top 25, I looked at how many total genes when the top 25 are picked up, and how many of those genes are unique. And what's interesting is that among the three configurations, about half of the SNPs were in a gene, and this is more than the baseline background rate for the entire data set, which was about 33%. But unsurprisingly, the LD 90% configuration had found many more unique genes. This isn't surprising because presumably in this data set and in this configuration, there's maybe only one or two SNPs in a given gene, where in this configuration you may have many SNPs in or near a given gene. Now, though, before we jump at the idea that this is the best configuration to use because it's a smaller data set, better computational efficiency, exact same prediction error rate, and finding more unique things, it is important to note that these are not perfect overlaps of sets. It's not as if this 7 unique genes are a direct subset of these 12. So each configuration is finding something slightly different, indicating that there is something to be gained from each of the 3 runs.
LD90 is taking out 10% of the SNPs?
Not 10% of the SNPs. When looking at a sliding window across the data set, looking at it, making sure there's no more than a 90% multiple correlation.
Did you look at tag?
Yeah, an R squared of 0.9.
Did you look at tag SNPs?
No, so yeah, no, I mean, in a more sophisticated way, there's definitely much more sophisticated ways of doing LD pruning than what's available in Planck. The main reason it was used was just for computational efficiency. Yeah, I mean, it would have been, yeah, I mean, probably if I was dealing with a smaller data set and more easier to work with, I would have done more of a tag SNP approach.
So how many SNPs are in the LD99?
That was about 160,000. So cut the data set size in half.
325?
Yeah, down to 160. Because this is an AFI chip. So there is going to be a lot more LD in the AFI chip.
So it's the size of 99.
I'm sorry?
How many 99?
In the 99, that was at about 2.5, so 250,000. So it's 320,000, 250,000, 160,000, 130,000. Yeah.
And this is on the LD of the patients or the controls or
Combined.
Perhaps not such a good idea, but you have to demonstrate that
Yeah.
you're not getting rid of SNPs that are differentially.
No, that is
differential to two groups.
yeah, no, that's actually a good point. Yes. So then at this point, I wanted to find out a way, can we go about confirming any of these results? And when you're dealing with an empirical data set, you can't always confirm results, but you can try and get a degree of confidence in your results. So the first test was a permutation test. And because initially when I did the subsampling process, my immediate thought was, I'm just fine, I'm actually overfitting the data entirely. I'm finding some weird multidimensional structure, and that's when I'm getting this really great error rate, and I'm just kind of zeroing in on it. So to do this, I just permuted case status and reran the same process, and actually, in fact, the error rate stayed consistently at 50%, as you would expect with a permutation, suggesting that there, in fact, was no overfitting. So that was very exciting.